So today we're going to be looking at practical applications of connected rates of change. So this is more practical uses for the chain rule that we looked at last time with rates of change. So let's just go straight in and look at some worked examples to show what we mean by this. So an oil is leaking from a pipeline. Under the pipeline under the sea, and a circular patch is forming on the surface of the sea. The radius of the patch increases at a rate of 2 meters per hour. Find the rate at which the area is increasing when the radius of the patch is 25 meters. So the oil leaking from the pipeline line, sorry, and as a circular patch forms on the surface of the sea. The radius, so you've got the circle on the top of the sea, and it's got some radius r, and the patch increases at a rate, the radius of the patch, so the radius of the patch dr by dt is 2. Obviously meters per hour. Find the rate at which the area is increasing in the radius of the patch when the radius of the patch is 25 meters. So we need to think, what is the area of the circle? The area of the circle is going to be pi r squared, and we want to find dA by dr by dt, sorry, when r equals 25. So we're going to differentiate the area with respect to r. So that's going to be 2 pi r. Now when r is 25, dA by dr is going to be 2 times pi times 25, and that will be 50 pi. Now we want, using the chain rule, the rate of change of r with respect to time is going to be the rate of change of A with respect to the radius times the rate of change of the radius with respect to time. And so we know dA by dr is 50 pi when the radius is 25 meters, and we know the rate of change of the radius with respect to time is 2, so we're going to times our 50 pi by 2, which will give us 100 pi. So the area is increasing at a rate of 100 pi meters squared per hour. Let's try another one. A solid sphere has a radius r centimeters, a surface area a centimeters squared, and a volume v centimeters cubed. The radius is increasing at a rate of 1/5 pi centimeters per second. Firstly, we want to find the rate of increase of the surface area when the radius is 3. That'll be 3 centimeters. And B, find find the rate of increase of the volume when r is 5 centimeters. So, firstly we're dealing with the surface area. So we need to find the rate of increase of the surface area, so dA by dt when r is 3. We know the rate of change, the rate of change of the radius is 1/5 pi centimeters per second. And we now need to find out what is the change of the surface area. So the equation for the surface area of a sphere is 4 pi r squared. So we're going to differentiate that with respect to r. So we'll get 8 pi r. And when r equals 3, dA by dr is going to be 24 pi. So I'll write it over here because I'm going to run out of space. So what is dA by dt when r is 3? It's going to be equal to dA by dr multiplied by dr by dt, and that's going to be 24 pi times 1/5 pi, which gives us 4.8 centimeters per second. So the surface area is increasing at a rate of 4.8 centimeters per second. Now B, we want to find, now we're dealing with the volume. So the equation for the volume of a sphere is 4/3 pi r cubed. And we want to find the rate of change of the volume with respect to r, so the derivative of v, is going to be 4 pi r squared. Now, when r is 5, dv by dr is going to be 4 times pi times 5 squared, which gives us 100. Oops. 100 pi. Now we're using the chain rule again. So the rate of change of the volume this time with respect to t is dv by dr multiplied by dr by dt. Now we know that when the rate of change of the volume when r is 5 is 100 pi, and we've already been told previously that the radius increases at a rate of 1 over 5 pi. So that's going to give us 20 centimeters cubed per second squared is the rate of increase of the volume. Now let's look at another example. So water is poured into a conical container, and we're going to sketch this. So here's our conical container, and here's our water, and it's at height h, and it's poured into the conical container at a rate of 2 pi centimeters cubed per second. After t seconds, the volume of the container of the water in the container is v centimeters cubed, and it's given by v equals a 12th pi h cubed, where h is the height of the water. So firstly, we want to find the rate of change of h when h equals 5. And secondly, we want to find, given the container has a radius of 10 centimeters and height 20 centimeters, find the rate of change of h when the container is half full. And we want our answer to that to 3 significant figures. So let's do A first. So what do we need to find out for this? We need to find out what dH by dt is when h equals 5. So volume is increasing at a rate of 2 pi centimeters cubed per second squared. So dV by dt is 2 pi. Now the volume is given by a 12 pi h cubed. And if we find dv by dh, that gives us a quarter pi h squared. When h equals 5, dv by dh is going to be quarter pi 5 squared, which gives us 25 over 4 pi. Now, using the chain rule, dh by dt is dh by dv times dv by dt. We know what dv by dh is 25 over 4 pi, but we want dh by dv, so we're going to inverse this. So it'll be 4 over 25 pi, and we know dv by dt is 2 pi. If we calculate that out, we'll get 0.32 centimeters per second for the change of the height. Now, let's do the second part of this. So the volume when half full will be 1/12, so it's going to be half of 1/12 pi h cubed. Now 1 pi 12, half of 12 pi. Now h is the height which we are given. The height of the cone is 20 centimeters, so it's going to be 20 cubed. And working all that, we'll get 1000 over 3 pi. Now, using the volume is a 12 pi h cubed, we know that this has to be equal to 1000 over 3 pi, and we can rearrange this to get the height cubed will be 4000. So the height of the water when it's half full, the height of that cubed is 4000, so the height will be 15.874 centimeters. So when h is 15.874, dv by dh must be, if we go back and look at what we had for dv by dh, we'll have a quarter pi, then 15.874 squared, and that gives us 197.9. Now we can use the chain rule to work out dh by dt is dh by dv times dv by dt. we have dv by dh here, so for this bit here we'll inverse it. Times 2 pi, which were given previously. Which were previously. And then calculate that all out, we get the change in height with respect to time as being 0.0317 centimetres per second. So I hope that makes sense.